Alright, here we go. We're going to talk about the next section, which is graphing exponential functions. So we're moving into something slightly new, so be prepared for that. Alright, so we're going to use some of the principles that we've seen before, happy joy, and try to establish this with exponential functions. I want you to understand what's the difference between a growth and decay function, and then also like being able to identify domain, range, and other stuff. So let's talk about asymptotes, or I'm sorry, graphing parent function. Now here's the parent. This is the parent function for a growth. Okay, notice that a growth goes up. Ooh, it goes up. Yes, it does. Okay, so we've got a function that goes up, and then we're talking about that it has an exponential growth goes up. There's an exponential decay, which would go down as you go from left to right. And then we want to make sure that, notice the domain, the range. But the main thing here, and I disagree with how they do this, but the main thing I also want you to see is that there is a boundary line that the graph looks like it's getting close to, but doesn't get close to, and that is called an asymptote. Okay, it's a line that the graph approaches. Now they're saying here the x-axis. I don't want y'all to ever use that. Okay, most of what we're studying here is going to be a horizontal asymptote. Later on we'll get to vertical. So we're going to say y equals. Horizontal is y equals. And in this case y equals 0. Most of your cases the y will equal 0, and then you kind of go from there. But for exponential functions, most of them are going to be horizontal lines. I have to really try something hard and weird to get it to be something different. Alright, so let's look at something here. Okay, so let's start off with something like f of x is equal to 3 to the x power. Now notice here that your variable is in the exponent position and you're going from there. Okay, so you got 3 to the x power. So anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. 3 to the third power is 27. But then you do negatives. Oh no, what happens with negatives? Negatives are going to give you fractions. So 3 to the negative 1 power is 1/3. 3 to the negative 2 power is 1/9. And yes, we will discuss what you have to do with those later. Okay, so then you do the graph. So notice that I like to start with this one on my, I don't want to say y-intercept, but let's think of that starting point. This point where if it had been 0, okay? And we'll discuss how we always move that. Traditionally, it starts at 1 because anything to the 0 power is 1. So usually if I want to make transformations to this graph, I'm going to base it off from that point and then draw my graph. Okay? So I'm graphing all the other points, and you can see there. This is how that graph would look. Notice how it starts off kind of low on the left side and rises on the right. Again, this idea is that this line is getting closer and closer to 0 without actually getting to 0. So there is my asymptote. So my domain is all real numbers because there is no limit to me going to the left or to the right, even though it looks like it's getting really close to a certain point. And then the range will be greater than 0. And notice how the asymptote and the range have kind of a similar relation. Alright? Notice that y equals 0 and f of x is greater than 0. Okay. Here are my different types of transformations. Okay. A is going to be the vertical reflections, or vertically stretching, compressing, so stuff that we've talked about before. If I want to move up or down, I'm using K. And if I want to go sideways, I'm using the H. And always think about it the opposite, because that one's kind of like if it was in parentheses. So let's look at an example of that. So here I have the 2x plus 1. If I wanted to see 2x, 2 to the x power, that's what I would have. It would go through 1 and be like that. So the plus 1, notice, moves it up 1 more. Okay? And now it goes through 2. So notice that it's going through that point at 2. So 1 higher. So everything got moved up 1 higher. So that means if my asymptote is at 0, now my asymptote is at 1. So let's look. So the domain. Notice how the domain, range, let's look at all those points. And there's my asymptote. Keep going, keep going, keep going. Okay, there we go. Okay, notice the domain still stays all real numbers. I mean, that's usually going to be the case until we get to some word problems, and we will cover word problems later. But notice how the asymptote and the range are actually increased by 1 because I moved it up or down. So the k is going to say change those. Whoops, maybe went a little too far on this one. All right, so let's look at this. Here is 3x plus 2. Notice that plus 2 means that one's in the h position, so that means it goes to the left or to the right, horizontal shift. All right, so plus 2, think opposite. Go to the negative side, so I'm going to negative 2. So I'm moving this point right here 2 spots over. Okay, and then basically I'm copying the same type of graph. You know, and so it kind of should look similar, and notice here how the domain and range is affected. In fact, the domain and range is not affected at all. It's just a matter of that it was shifted to the left or to the right. And the asymptote would also remain the same. So kind of notice how the asymptote and the range were affected, and they were only affected when it was with the plus or minus the k. If you hear any other background in the music, that's just some say little munchkins playing some water polo and being very loud because, well, why not? Okay, so let's look at this one. This example contains all of the types of transformations you could have. I mean, maybe not like necessarily what you can necessarily do. I don't have a reflection here, but you get the idea. Anyways, all right, so notice here I'm starting at 1 because most of our times when we say anything is to the 0 power, it starts at 1. Okay, so that's like my standard point. But from there, I can pretty much what I want you to do is kind of figure out from there. So the minus 3, the x minus 3 exponent means I'm going to go to the right 3. So I went to the right 3. And then the minus 2 means I'm going to go down 2 spots. And then, to be honest, the 1/2 would make that kind of change that up a little bit and adjust that a little bit. And I can kind of see that, for example, here, that at 3 I ended up at negative 1.5. So, but it gives you a good rough idea. I pull out the table so you can kind of see what happens here. Notice how as I'm going higher or I'm going lower on the x, my numbers are getting closer to negative 2. So that kind of confirms. Notice how that will end up being my asymptote. And that's kind of the important part because really what I want to see is more of this curve that you're seeing me draw and that you show that you know where that asymptote is. That kind of gives you a better idea of where it would be. So let's look at the domain and range of this. So the transformations here, and I'm showing it all to you, notice the domain is still all real numbers. The range is greater than negative 2, so notice that relation between k and the range, and the asymptote is at y equals negative 2. That is the boundary line. That is the line that that graph would approach but not get there. Now, transformations, you already see that I've said right 2, or right 3, down 2, and say compress. Now notice, the green is what would be a normal exponential function. Compress, notice, lowers that part that's going up and kind of flattens it out a bit. That's what it means to be compressed. Okay, so I kind of wanted you all to see that. Whew, I've covered a lot here and I've taken quite a few minutes. Okay, so now let's look at decay. What is decay? Decay means it goes down. How do I make it go down? You would think a negative. No, but it's not a negative. What is that makes it go down? It is the fact that it is between 0 and 1. What does that mean, sir? It means I can give you more fractions. So let's do some fractions. You know me, I don't like decimals, so there you go. All right, so 1/2 to the 1/2 x power. Okay, so 0, 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/4. I mean, that's basically what these numbers are. Notice that the negatives become the bigger numbers. Why did I put negative 4? That's not a negative 4. Oops, that's a positive 4. Good grief, I'm just slow today. Anyway, so you can see the graph, and notice there's a decay. Notice that it started out high and went down. But look at the domain, range, and asymptotes. So they don't really make that many changes. So my idea here is that I want y'all to be able to identify if it's a growth or decay, know your domains, know your ranges, know your asymptotes, and how can you find them. And that's what we're going to start out with. And then we're going to start seeing how these types of functions get applied to different types of applications, such as population control and growth and things like that. All right? So kind of give you an idea. Here's another example. Transformations. Notice that the 1/4 or the 1 over whatever, can't see, sorry, 1/4 is not being really anything. It doesn't affect the transformations themselves. The numbers that you see on the outside still tell us what we're kind of doing. So, and look, I'm not doing a very crazy graph here. I do want a rough graph, but notice I'm going to be specific. Oops, didn't mean to erase that. I'm going to be specific about how you show me asymptotes, domain, range, things like that, and describe to me transformations. Anyways, that's all for today. Thank you so much. Y'all be great, and I will see y'all later. Take care.